Look up at the night sky. What do you see? Countless stars scattered across the darkness. Each one is a distant sun, many with planets of their own. The universe is vast and mysterious, full of wonder. For centuries we have asked big questions about the universe. How did it all begin? How big is it? What is it made of? Over time, we have developed incredible tools and theories to help us understand the cosmos. This journey of discovery is a testament to human curiosity. From ancient astronomers to modern physicists, we've come a long way. In this exploration, we'll delve into fascinating theories about the universe's origins, workings, and ultimate fate. Our ancestors observed the sky with awe and fear, seeing patterns in the stars and telling stories about them. These stories became myths and legends, explaining the world and their place within it. The ancient Greeks developed models of the universe based on observation and reason, believing Earth was the center of everything. This geocentric model prevailed for centuries. Ptolemy, an influential astronomer, created a model that predicted planetary movements with surprising precision. However, some thinkers, like Aristarchus of Samos, proposed that Earth might revolve around the Sun. These heliocentric ideas were largely ignored for many centuries, but the seeds of doubt had been sown. In the 16th century, Nicholas Copernicus revived the heliocentric model, arguing that Earth and other planets revolved around the Sun. His ideas met resistance, especially from the Church. Galileo Galilei further challenged the established order with his telescope observations, providing strong evidence for a heliocentric universe. Despite conflict with the Church, the scientific revolution had begun. Johannes Kepler refined Copernicus's model, showing that planets move in elliptical orbits. This period marked a turning point in our understanding of the universe. It paved the way for even more revolutionary ideas. Imagine the universe concentrated into a single point, smaller than an atom. About 13.8 billion years ago, this point began to expand rapidly in a massive explosion of energy and light. This is the Big Bang theory. The Big Bang wasn't an explosion in space, it was the expansion of space itself, like a balloon being inflated. Georges Lemaitre, a Belgian priest and physicist, first proposed this idea, calling it the hypothesis of the primeval atom. Initially met with skepticism, mounting evidence solidified the Big Bang as the leading explanation for the origin of our universe. The journey of discovery continues. One key piece of evidence for the Big Bang is the redshift of light from distant galaxies. Light waves stretch or compress depending on their motion, similar to the sound of a siren changing pitch. Observing light from distant galaxies, astronomers noticed a redshift, indicating that galaxies were moving away from us. This implied that the universe was expanding, just as predicted by the Big Bang theory. Another piece of evidence is the abundance of light elements like hydrogen and helium, formed in specific ratios during the early universe. These observations support the Big Bang model. The universe is dynamic and evolving. Edwin Hubble, an American astronomer, discovered the expanding universe in the 1920s. Using the Hooker telescope, Hubble measured distances to galaxies and compared them to their redshifts. He found that the farther away a galaxy was, the faster it was moving away from us, known as Hubble's law. This discovery revolutionized our understanding of the universe, providing concrete evidence that it was dynamic and expanding. Hubble's work laid the foundation for the Big Bang theory to gain widespread acceptance. It also gave us a way to estimate the age of the universe. The current estimate is around 13.8 billion years. The cosmic microwave background, CMB radiation, is compelling evidence for the Big Bang. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the CMB is a faint afterglow of the Big Bang. This afterglow permeates all of space, providing a glimpse into the early universe. The CMB corresponds to a temperature just above absolute zero, the cooled remnants of the early universe's intense heat and energy. Its discovery provided direct evidence for the Big Bang theory. The CMB is like a baby picture of the universe, a snapshot of its early stages. Its properties have provided scientists with a wealth of information about the universe's evolution. Imagine a bowling ball on a trampoline creating a dip in the fabric. This is a simple analogy for how gravity works according to Einstein's theory of general relativity. Einstein proposed that gravity is a consequence of the curvature of space-time. Massive objects like stars and planets warp space-time around them, affecting the motion of nearby objects. Planets orbiting a star follow curved paths through warped space-time. Einstein's theory has been confirmed by numerous experiments and observations. It accurately predicts phenomena like gravitational lensing and shifts in planetary orbits. One of the most mind-boggling predictions of general relativity is the existence of black holes. These regions of space-time have gravity so strong that nothing, not even light, can escape. Black holes form when massive stars collapse, creating a point of infinite density called a singularity. Surrounding the singularity is the event horizon, the point of no return. Black holes are invisible to telescopes, but their presence can be inferred by their gravitational effects on nearby stars and gas. Scientists have discovered black holes of various sizes throughout the universe. From stellar mass black holes to supermassive ones at galaxy centers, they are a testament to the power of gravity. While general relativity describes the universe on a grand scale, quantum mechanics delves into the bizarre world of atoms and subatomic particles. In the quantum realm, particles exhibit wave-particle duality, behaving both like waves and particles. Heisenberg's uncertainty principle states that we cannot know both the position and momentum of a particle with perfect accuracy at the same time. Quantum mechanics explains the behavior of atoms and the interactions between light and matter. It underpins many modern technologies, including lasers, transistors, and medical imaging devices. The quantum world is a realm of uncertainty and strange behavior. It has profoundly impacted our understanding of the universe. Scientists have identified four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Quantum mechanics describes three of these forces, but gravity remains the odd one out. The quest for a unified theory, or a theory of everything, is one of the biggest challenges in modern physics. Such a theory would provide a single framework for understanding all the forces of nature. Promising candidates include string theory, which proposes that the fundamental building blocks of the universe are tiny, vibrating strings of energy. However, a complete and experimentally verified theory of everything remains elusive. The search continues, driven by the desire to unravel the deepest mysteries of the cosmos. Imagine observing a galaxy spinning in space. You'd expect the stars further out to move slower than those closer in, but they don't. Astronomers noticed that the stars on the outer edges of galaxies were moving much faster than they should have been, based on visible matter. It was as if there was some invisible mass, some dark matter, holding those stars in their orbits. This discrepancy suggested that there was much more to the universe than meets the eye. Dark matter doesn't interact with light, making it invisible to our telescopes. Its presence is revealed through its gravitational effects on visible matter. Dark matter is a form of matter that doesn't interact with light or other electromagnetic radiation. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. We know it's there because of its gravitational effects on stars and galaxies. The leading candidate for dark matter is a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are thought to be heavy, slow-moving particles that interact with normal matter only through the weak force and gravity. Scientists are actively searching for WIMPs and other potential dark matter particles using various experiments. The search for dark matter continues, driven by the desire to understand the invisible hand shaping our universe. Fast forward to the late 1990s. Two teams of astronomers were studying distant supernovae, exploding stars that briefly outshine entire galaxies. Supernovae are like cosmic lighthouses, their brightness allowing astronomers to measure vast distances across the universe. The astronomers expected to find that the expansion of the universe was slowing down over time due to the gravitational pull of all the matter in the universe. After all, gravity is an attractive force that pulls things together. But what they observed was the complete opposite. The distant supernovae were fainter than expected, suggesting that they were farther away than they should have been if the expansion of the universe was slowing down. In fact, the expansion of the universe wasn't slowing down at all, it was speeding up. This discovery, which earned the astronomers the Nobel Prize in Physics in 2011, sent shockwaves through the scientific community. It meant that there was something else out there, something mysterious and powerful, counteracting the pull of gravity and pushing everything in the universe apart at an accelerating rate. Scientists have dubbed this mysterious force dark energy. It's thought to be a property of space itself, a kind of cosmic anti-gravity that pushes everything apart. Imagine blowing up a balloon and noticing that the more you inflate it, the faster it expands. That's kind of what's happening with the universe, with dark energy acting as the inflating breath. The nature of dark energy is one of the biggest mysteries in modern cosmology. We don't know what it is, what it's made of, or why it exists. One possibility is that it's related to the cosmological constant, a term that Einstein introduced in his equations of general relativity to represent a kind of energy inherent in empty space. Another possibility is that our understanding of gravity is incomplete and that we need a new theory of gravity to explain the accelerating expansion of the universe. Whatever the explanation, dark energy has profound implications for the fate of the universe. If dark energy continues to dominate the expansion of the universe, as current observations suggest, then the universe will continue to expand forever, growing colder and darker over time. Galaxies will drift farther and farther apart, eventually becoming isolated islands in the vast cosmic void. The discovery of dark energy has fundamentally changed our understanding of the universe, raising more questions than answers and pushing the boundaries of our knowledge to the very edge of the cosmos. Our universe, vast and awe-inspiring as it is, may not be the only one. This is the mind-boggling concept of the multiverse, the idea that our universe is just one of many universes coexisting alongside each other. Imagine a vast cosmic ocean filled with countless bubbles, each bubble representing a different universe with its own unique properties and laws of physics. The idea of the multiverse might seem like something out of science fiction, but it arises from several theoretical frameworks in physics and cosmology. One such framework is inflationary cosmology, which describes a period of rapid expansion in the very early universe. Inflationary theory suggests that our universe underwent an exponential growth spurt in the first fraction of a second after the Big Bang. This rapid expansion could have created regions of space that inflated differently, giving rise to separate, self-contained universes with potentially different physical constants and laws of nature. Another route to the multiverse emerges from string theory, which we'll delve into later. String theory proposes that our universe has extra spatial dimensions beyond the three we experience. These extra dimensions could be curled up and hidden from our view, and they could potentially host other universes, much like pages stacked within a book. Many worlds, many possibilities, exploring the implications. The implications of the multiverse are profound and mind-boggling. If our universe is one of many, it questions the uniqueness of our existence. Are there countless versions of ourselves in parallel universes? The multiverse challenges our understanding of reality and the Big Bang. It stretches our conception of reality to its limits. String theory, a symphony of strings. Imagine the universe not as a collection of point-like particles, but as a cosmic symphony of tiny, vibrating strings. This is the essence of string theory, a theoretical framework that attempts to unify all the forces of nature and provide a complete description of the universe from the smallest subatomic particles to the largest cosmic structures. String theory proposes that the fundamental building blocks of the universe are not zero-dimensional point particles, but rather one-dimensional extended objects called strings. These strings are incredibly small, far smaller than anything we can currently observe with even our most powerful particle accelerators. Just like a violin string can vibrate at different frequencies to produce different musical notes, strings in string theory can vibrate in different modes, giving rise to the different particles we observe in the universe. The electron, the quark, the photon, and all the other fundamental particles are thought to be different vibrations of the same fundamental string. One of the most intriguing aspects of string theory is that it requires extra spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions are thought to be curled up and compactified, hidden from our perception. The geometry and topology of these extra dimensions play a crucial role in determining the properties of the particles and forces in our universe. Section 4. Unifying the Universe, the Promise and Challenges of String Theory. String theory holds the promise of unifying all the forces of nature, including gravity, which has resisted unification with the other forces in the standard model of particle physics. In string theory, gravity emerges naturally from the vibrations of strings, just like the other forces. This unification of gravity with the other forces is a major achievement of string theory, as it offers a potential solution to the long-standing problem of reconciling general relativity with quantum mechanics. These two pillars of modern physics have been notoriously difficult to reconcile, as they describe the universe on vastly different scales and with seemingly incompatible principles. However, string theory is not without its challenges. One of the main criticisms is that it has yet to produce any testable predictions that could be verified or falsified by experiments. String theory operates at energy scales far beyond the reach of current particle accelerators, making it difficult to test its predictions directly. Despite these challenges, string theory remains one of the most active and exciting areas of research in theoretical physics. It continues to inspire new mathematical tools and concepts, and it offers a glimpse into a deeper level of reality that could revolutionize our understanding of the universe and our place within it. Section 1. Our place in the cosmic symphony. Our exploration of the universe has taken us from the fiery birth of the cosmos to the bizarre realms of dark matter, dark energy, and the multiverse. We've encountered mind-boggling concepts like warped space-time, quantum uncertainty, and vibrating strings of energy. It's a journey that has expanded our understanding of the universe and our place within it. Section 2. The Unending Quest, Future Frontiers of Cosmology. Despite all that we've learned, the universe remains full of mysteries. We still don't know what dark matter and dark energy are made of, or why the universe began with the Big Bang. The quest to answer these questions is driving a new era of cosmological exploration. Scientists are developing ever more powerful telescopes, both on Earth and in space, to peer deeper into the cosmos and observe the universe's faintest light. The future of cosmology is bright with promise, and the next few decades are likely to bring about transformative discoveries. Section 3. A universe of wonder and humility. Our exploration of the universe is both scientific and philosophical. It reminds us of our small place in a grand cosmic symphony. Life on Earth contemplates the universe with wonder and humility. The universe is full of wonders, inspiring awe and self-discovery.